again, think about what is the objective, what are the decision variables, and what is the constraints on the system. So what's the objective?
To minimize total cost.
Minimize total cost, exactly. What's the decision you as a production planner need to take, or what are the sets of decisions that the production planner needs to take in order to minimize cost?
When to get your inventory most efficiently?
Okay, inventory has something to do with it, but let's be specific in terms of the decisions so that we can define variables from those decisions.
Minimize holding cost.
Okay, so they are talking about minimizing, which is an objective.
Yeah.
So that's an objective, minimizing holding costs. It's part of the objective, right? We want to minimize total cost, which is production as well as inventory. So the question is, how do we minimize? What decisions do we make to minimize total cost?
Which week we're going to purchase how much?
Produce, not purchase.
Okay.
Produce to demand. Yeah, exactly. So how much do we produce? So that's one set of decisions. How much do we produce in each week? What's the next set of decisions? How much to hold in inventory at the end of the next week, at the end of that week, right? So that's what we're going to define our decision variables as. Oh shoot, don't tell me my thing is dead. Anybody else has a Microsoft stylus?
Yeah.
Thank you. Thank you. Okay. This is a nice heavy one. Should get one like this.
So no, yeah, they're great.
Is it the 2.0?
Yeah, it's, I don't know, it's got more grip to it.
So our first set of decisions is how much to produce in each week. And then the second set of decisions is how much to hold inventory at the end of that week. How do you use a razor on this?
You just
job?
flip it over and erase.
Like this? Oh, nice. So, how do we write the objective now as a function of the decision variables? We know that we want to minimize total costs And we just take the cost for producing in week 1 multiplied by the amount of units we produce in week 1, and we keep adding the costs together for all 3 weeks for production, and then add the inventory costs. Remember, the inventory holding cost for each week is just $1. So all I'm doing is I'm just adding how many units of inventory I have, and that's the number of dollars of inventory holding costs I have to pay, right? Then I have to figure out what my constraints on the system are. So we must produce enough to meet demand each week, right? We can either meet demand by producing or by satisfying the demand from inventory, right? So if we produce in excess of demand, that goes into inventory, right? So basically inventory is everything that goes into production, that comes out of production and does not meet demand, right? So let's write out in that logic. So the inventory at the end of the first period is equal to the amount we produce in the first period less the demand, right? But since we cannot have any, we can only have a constant on the right hand side or a real value on the right hand side, we rewrite it so that we have all of the decision variables on the left hand side and just the constant on the right hand side. This is what our constraint looks like. What about for week 2? What is the amount of inventory that we have in week 2?
I1 plus P2.
So how much we produce in week 2 plus the amount of inventory left over from the week 1, right? And less the amount of demand in week 2. And similarly for week 3. So I think about the constraint in a particular way in terms of how much inventory I have left over at the end of the week, and then I rearrange the terms so that it actually looks like a constraint that I can enter into a tableau, right, into the matrix form. So the restrictions that I have are, the variables are all non-negative. And then I put everything together so that it looks like this. And for those of you who want to do it, you can go ahead and put it into the Tableau format next. And once you've put it into the Tableau format, think about the next scheduling problem that we're going to solve, which is the Mac computers. How much do we need for each of the 6 months in the next problem that we're going to solve? That's what we're going to learn today. Excellent. So what we're going to learn today is how to take that tableau, put it into an Excel sheet, and solve it.
step on one, is that variable reactions?
Restrictions.
Restrictions. Oh, sorry.
Yeah. In chemistry, you might have had a reaction, but so if you download the Excel companion file for this lecture, and you can do that now, you will actually see all the examples that we've done in that Excel file. Each tab has got one of the examples, and we're actually going to work on the wire products example to see how we can solve these problems using Excel. Okay? That's what we're going to do in the second part of this class. And you need that for your homework on Thursday. So we definitely need to finish that before we leave here today. Okay, so hopefully you got a chance to look at the scheduling example. We've got 6 months worth of scheduling requirements in terms of machines, max that we need. We have 3 different contracts. So the question is, first question, what is our objective? Minimize costs, right? Again, now, what is the decision that we have to make to minimize costs? We're not producing anything. Sorry? Okay. So that's part of the decision, right? So how long do we want to rent the computers for? But let's think about the decision as a whole. What is the decision that we have to make? Exactly. How many computers to rent in each month and for how long? Okay? So we can define those 2 decisions in one variable very easily. I use M to signify max. And I use 2 subscripts. The first subscript I is which month we are going to rent in. And the J is how long the contract is going to be. So we'll define that as number of max So there are 6 months. So the I subscript can take on a value from 1 through 6. The J subscript is representing the number of months the contract is going to run. So we know that there are 3 contracts, a 1 month, 2 month and 3 month contract. So the J subscript can take on 3 values, 1, 2 and 3. Okay. So in total, how many expressions are there? We have 6 months, and each month we can have 3 contracts, right? So 18, right? And that's the idea of writing it. So we have 18 expressions. We can now, we have 2 summands. One is for the number of months from 1 to 6, and the other one is for the length of the contract. Okay? So we know that we have 18 of these expressions. Now, the cost regardless of the month, a 1 month contract is going to cost the same. A 2 month contract is going to cost the same, and so on and so on. However, you can clearly see if I gave you contracts that had a different price based upon the month in which you rented, then you would need 2 subscripts for the cost as well, right? Yeah? Because now the cost would change based upon the month. But now the cost does not change based upon the month. So you just have those 3 costs, and that's why you have the J subscript alone, which represents those 3 values. Yeah? So, in terms of the constraints, this is how we construct the constraints. So for the first month, all I'm doing is I'm taking the first month on a 1 month contract, 2 month contract, and 3 month contract, taking the number of computers that we could rent and adding them up together, and I'm saying they can be greater than or equal to the amount of demand for that month. Now, why is it greater than or equal to? Because it might so happen that I might have more computers rented earlier on a longer contract that are cheaper to have, right? So that's the rationale behind it. So for the second month, I do the same thing. I take second month contracts, add them all up, but I also have the 2 month contract from the first month and the 3 month contract from the second month that carry over into the second month, right? For the third month also I have the same thing, the 1, 2 and 3 month contracts for the third month, but now I have my 3 month contract from the first period, my 2 month contract from the second period, and my 3 month contract from the third period. And basically this is how I keep constructing my constraints. So for a small problem like this, we can write this out by hand. But if we have a large problem, if we have to say schedule a 6 month contract with Ernst & Young, and we have 1,000 employees, and the number of employees and the number of computers will change, then clearly we have to write out a program, right? We have to write out a program where we have to set up every single variable, and that program is now going to cycle through and create all of these expressions for us. Okay? So when you do something like that, you will realize that there will be a lot of redundancy that you can probably reduce. So for example, here, what are some of the expressions that you don't require? What are some of the variables that are probably redundant over here? Think about the length of the contract.
The contract could span multiple months.
Okay? Okay? So, I'll give you a clue. A 1 month contract gets over at the end of that month. We don't have to worry about that. But a 2 month contract and a 3 month contract can extend beyond that month, right?
But the rest of that contract,
Yeah. Yeah, so think about that. Think about that in the context of, do we need all these variables? Which ones do we not need? It still costs us, right? And the 1 month contracts are still used to fulfill that demand, right? So we need those. We can't eliminate those.
but you can't eliminate the information of the contract is spanned over multiple months that bleed over into the month that you're trying to calculate.
Okay.
But can you simplify it?
So let me ask you this question.
Do we need to go to month?
The months are given to you. January, February, March, April, May, June. The variable. So let's say, hypothetically, all of you all needed to rent a computer for doing simulation in February and in March, right? And you had a vendor that was giving you a contract for a 1 month, 2 month, or a 3 month rent, right? Would any of you pick a 3 month rental agreement? Why? You don't need it, right? Why would you have a 3 month contract when you're going to run out and not have any use for the computer after that? So, in that same way, in the 6th month, do I need a 3 month contract? No. Do I need a 2 month contract? No. Right?
So this is like assuming that there are no contracts past June.
No. The contract gets over, right? We only need it for 6 months. I don't need a 3 month contract in my second last month either. And so I can eliminate that as well. I don't need a 2 month contract in my last. Oh, this one I need. I'm getting ahead of myself. Right? Is that clear? So that's how you can simplify. So for large problems, you will probably have to write a program to list all the different decision variables, and now you will have to go in and eliminate some of these decision variables. So then, how do we restrict this? What are the restrictions? We know that we have to use positive integers, right? Which we know we can also write as Mij belongs to the set of all positive integers. So, when you put it together, I think you already have it in your notes. It's going to look a lot like this. So, when we don't have any need for those decision variables, we simply delete them without compromising how we solve the problem. So that's an example of inventory, production, scheduling, transportation. These are some of the broad classes of linear programs that are out there. We already talked about this with the transportation problem. This is just another illustration for it, for your notes. Here are some of the rules summarized for you. Yeah.
Why wouldn't constraints include stuff that's just greater or less than without the equals to?
That's just how the heuristic works. So the not the heuristics, the algorithm. So the algorithm has to be greater than or equal to. So say, for example, you want your constraint has to be greater than 100. Okay? You can set it equal to 100.1.
No.
Greater than or equal to 100.1. So everything greater than 100, you can set it equal to greater than or equal to 100.1. So that's a way of getting around that. But the way the algorithm is read up, the simplex algorithm is set up, it has to be greater than or equals to. Okay?
Okay. Yeah.
And so here's the Lego problem where we all started. Okay? So now we know what the objective is, right? We want to maximize profit. You all did that. But while you are maximizing, what were you doing to maximize profit? So that's a decision that you have to make, right? What's the decision variable? What were you doing to maximize profit?
Deciding tables or chairs.
Be more precise, Joe. How much tables to produce and how many chairs to produce, right?
Yeah.
So that's our decision variable. We know we have to restrict it to be an integer. What's our system constraints? So that's one, labor hours. Raw materials, small and large bricks, right? So we have three resource constraints. Okay? It's a typical production problem. Okay? We're going to learn how to solve this in Excel. So in your notes, I've given you examples of screenshots that are that we're going to follow through right now. If you want, you can go to eCampus and download the download the Excel solver file so that you can reference it. See if I have this working. So we're going to go through the production planning example. First, I want to show you the Lego example. So that's all set up for you over here. You have the formulation, which is maximize the profit. And again, here, the profit is not given to you. You have to calculate the profit, which I'm sure a lot of you did when you were doing your the actual manual exercise. And these are the formulations for the constraints. Okay? And you have to solve the public and the military separately. So here you have the profit, or in this case is the selling price, and then the profit is calculated automatically from the sales price. So right now it's set up for the military, and then when you want to change it, put the public table and chair selling price in there, and then you can solve it. So what we're going to do today is we're going to solve the wire products example. Now in your homework I've said refer to this Excel spreadsheet. This is how you need to format it for a number of different reasons, as hopefully become apparent as we go through. So I use a red outline to indicate what my changing cells are. Okay? Now also notice that I've included column headers not only for the changing cells, also for the actuals column, which I'll go through in a second, but also the right hand side column, and I've highlighted that blue. Okay? Then for the coefficients, I've included a blue outline for all of them, with a blue outline only indicating what my objective coefficients are. I've got a gray outline for what's called the objective actuals, which I will talk about in a second. So this is basically how you want to set up your solver inputs for solving the objective solving the linear program. These row labels as well as the column labels or headers are used by Excel in the reports that are generated to identify what the solutions are, the different parts of the solution. I put the max over here to remind me what I'm doing, and the relations over here, these are just text entries. The reason I put these in is when I'm setting it up in Excel, it helps me to identify what the constraint is so I don't have to memorize everything. For a small problem like this, it's not a problem, but when you have a big problem with 30 or even more constraints, then you don't have to sit and memorize what each row is. As I said, on the right hand side, these are just values that are entered. So you can see this is 6, 10, and 15. These are just plain values that I inserted without any decision variables or any formulas whatsoever.
That's what I was going to ask.
Yeah, you can't put any formulas on the right-hand side. Okay, so the actuals. So you see in the actuals, they all have a formula called the sum product. Okay, so what is the sum product? If you look at the sum product, it requires two inputs. It requires two vectors, or two columns, or two rows. I like to call them vectors because it's a line of numbers, basically, a list of numbers. So one vector has to always be anchored. That's why I use the $ to anchor it for row 4. It always has to be anchored on the decision variables. Okay, and the other one will be anchored based upon whatever row you are calculating the actuals for. In this case, I'm calculating the actuals for the objective function. And the way the sum product works is I take the product of these two cells, these two cells, these two cells, and these two cells, and I add all of the products up. That's the meaning of sum product. Okay? So right now, the value over here is 0 because there are zeros over here. Okay? So if I were to enter 1 in here, you will see that because of the sum product, now all I'm getting is a sum of all of these values, okay? Because I'm multiplying them by 1. In the second, third, fourth, for the 3 constraints, I have the same formula, which you can see is now the coefficients of this constraint multiplied by the decision variables. So remember, the objective and the constraints are just functions of the decision variables. So what we're using the sum product for is to show the function of that particular constraint or that particular objective function as a function of the decision variables, right? And that's what the sum product helps us to do. So it's very easy as long as we are pointed to this row of decision variables and we've anchored it, we can actually just drag this down . And that's just going to stay the same, okay? It's going to stay fixed because we've anchored it. Okay, so that's how Excel now recognizes what is the objective, what is the constraints. The next step is to actually start inputting it into Excel. Get to Abraham's question about what's the point of the tableau, right? So this is the tableau now, what do we do? So if you click on the data tab, then you should have solver here. Now, if you're following along, does anybody not have solver on their data tab? All right. So most of you are not going to have solver on the data tab. The way to get solver is to click on file and scroll down to options. Okay? Then this brings up this menu. Now you want to click on the left hand side on add-ins. Okay? That brings up this window. In this window you've got to go down to the button that says go with the abscissors. Click on that go and it'll bring up this menu window. Now for me, the solver add-in is checked because I have solver, as you can see, solver is listed over there. So my solver add-in is already checked. If your solver add-in is not checked, just check it. And once you've checked it, hit OK. And then Excel will start installing it. Okay, you don't have to do anything. It's already built into it. It just doesn't load automatically. You have to load it manually. When it's loaded, then you will have solver that's added to your data tab, right? So once you have solver added, then you just click on solver, and this is what the solver entry window looks like. The first field that needs to be entered is the objective. So we need to set what the objective is. So I click on that button on the right side of that field, and then I point to the actuals that calculates what my objective function is. Okay? Once I've done that, I hit OK. Then the next thing to do is to tell solver what we're doing. We want to maximize, minimize, or we want to get a certain value. Okay? In this case, we are satisfied by just doing maximize. The next field is the changing cells. The changing cells are our decision variables. So now, this is why it's helpful to highlight, because now I just can see what my changing cells are, and I highlight all of those changing cells at once, and I now get an input of a range of changing cells. Okay? Now to adding my constraints. So I can again click on this. It becomes actually, so let's do that. So this is my constraint. Why is it not? And then the next entry is my relation. So either less than or equal to, greater than or equal to, or equals to. So I'm happy with less than or equal to. I'll come to the other points a little bit later. And then my right hand side, which is the constraint, I can simply input it directly. I don't have to click on that. You can just go here, and then I can add another constraint. Now, the nice thing about about Excel is if everything's lined up nicely, then I can just highlight all of the constraints if all my constraints have the same relation, I can just add all of them in together. So I add the left-hand side, then the relation is still less than or equals to, and then I add the constraint, and this becomes really useful when you have to add in, say, for example, when you're doing facility location or transportation scheduling, you have 30 constraints. It becomes really simple to do this. Okay, you don't have to sit and manually do it every 30 times. So then I say OK, and now clearly I have this constraint that is redundant, right? So I just delete that.
That was the first one that you made, right?
Yeah, that was the first one, but now I've added all the constraints in one go, right? Now say, for example, in this case, we know that, most of our cases, we know that all variables have to be non-zero, right? So here it says, make unconstrained variables non-negative, okay? So that means that all the variables are going to be non-negative, okay? So let's just make that all variables non-negative. What if we had to restrict, in this case, of course, in our production example, we know that we don't have to restrict it to integer values because they are thousands of square feet, right? Yeah? So what if it was integers? How do we add that constraint? So we now have to go in and we have to add a constraint where we say these decision variables they all have to be, in this case I select integers, okay, int. So when I select this, you'll see that in the right hand side box Excel automatically adds integer in there, okay? So there's no need to enter anything. You say okay, and you'll see that that constraint is added, okay? Now in this case we don't need that constraint because it can be we can have decimal values, so all I do is just delete that. Now the last part is selecting a solution method. Now you can see this is the GRG nonlinear. Now this is the nonlinear algorithm. We don't need to use a nonlinear algorithm. Actually, we don't want to use a nonlinear algorithm. We want to use a simplex linear program, the linear method. Okay? So this is, we are always going to use the simplex LP for solving our problem. Now, if you made a mistake, then you can just hit reset all. Don't worry about the load and save. It just allows you, if you have multiple models on a sheet, Excel is a little bit finicky, so I'm not going to go through that. We're not going to require multiple models on a sheet where you can solve and load multiple models. A quick look at the options. These options are mainly used for large scale and for integer programs, binary programs, like we're going to learn about next class. Okay, and of course these values, these options are for nonlinear. And evolutionary, the genetic algorithm is for very, very large problems that cannot be solved easily using either the GRG nonlinear or the simplex. Now, we're not going to get to that point, so we're not going to bother about that. If you want to look at problems like that, then come back and do the data analytics class. Okay? The master's of data analytics. That's where you learn stuff like this. Okay. So, everything is set up. Now, all we have to do is hit solve. When we hit solve, we are telling solver the program is left to solve. If, when you hit solve, it comes back and says infeasible solution, that means one of your inputs is wrong. Okay? So, when you hit solve, you should get this solver results window. Ask you to keep the solver results or restore original values. Usually it's, you want to keep it. You can also highlight the answer report and the sensitivity report. The limits report I've given you a little bit of a write-up on. It's really used only for non-linear programs. You can save the scenario, okay, which because we are dealing in such small problems, you really don't need to. So when you hit OK, you're going to see two more sheets added to the workbook. Let's start with the answer report. Answer report gives you the basic feedback on all the different informational items about the workbook, who's created it, when it was created, etc., and what was the solver engine used, how much time was used, how many iterations did it take, etc. You can see that in the solver report, the labels are used. So you can see the objective, max, objective, actual. You can see what the original value was. Remember, because we put in values of 1 right throughout, so that was the original value. This is the optimal value. It's telling us that our maximum profit is $3,400. Okay? So what is our solution? So here you can see the variables. These are the variables that we labeled each of those columns with, and these are the original values. This is the optimal value. So we make 4,000 square feet of industrial cloth and 2,000 square feet of insect screen and nothing of roofing mesh and snow fence. That's the optimal solution. Okay? Those variable values, and here you can see it's not an integer, these are continuous variables. Okay? Then comes to the constraint report. Again, the names are used from the rows that we gave. We have the cell values. Now these cell values are the actuals that are reported at the end of the solution. So you can see that we've used all 600 hours of the wire machine. So that's a binding constraint. Okay? We have no more slack hours of that particular resource. We've used all 1,000 hours of the loom. That's a binding constraint. And so there's no slack. However, we've only used 10 hundredweight of aluminium. Okay? So that's not a binding constraint, and we have 5 hundredweight slack. Okay? So now, all of this information, we can just go to the sheet and we can look at it and find it. This becomes really invaluable when you have a very large problem with thousands of variables, with hundreds and thousands of constraints, and then it's very easy to just go down this list of this report and find which variables are part of the final solution. So you can see that these variables are part of the final solution, and what is the slack and binding and non-binding constraints. And the reason why we are interested in non-binding constraints will be apparent when we look at the sensitivity report next. Okay? So any questions about this so far? Okay, let's take a look at the sensitivity report. So we have two parts of the sensitivity report. We have the variable cells and the constraints. Now, let's see if I can increase this. Can you see this at the back? So let's take a look at the first one. So here we have the final values, right? So we know that we have 4 units and 2 units of industrial cloth and insect screen produced. We know that there's nothing of roofing mesh and snow fence. The next column is something called reduced cost. You'll notice that for the variables that are part of the optimal solution, there's no reduced cost. The ones that are not, there's reduced cost for them. So each linear program software has got its own idiosyncrasies. The negative values for a maximized profit is one of the idiosyncrasies of Excel, unfortunately. How do we interpret this? So here what they're saying is that there's a reduced cost for it because if you increase the objective coefficient by 5.7 units, that is, if you make $570 in profit, then roofing an additional $570 in profit. So in other words, you make $9.5 or $950 in profit for a roofing mesh, then roofing mesh is now going to become part of the optimal solution. Does that make sense? So forget about the negative value here. Since we are maximizing profit, we have to increase the current profit value of roofing mesh by 5.7 units. I'm using hundreds of dollars because that's what the profit's in. So I have to change the roofing mesh from 3.8 to 3.8 plus 5.7, which is 9.5, right? In order for roofing mesh to be produced and become part of the optimal solution. Yeah? Similarly for snow fence, I need to increase the profit from 4 to 8 by an additional 4. Okay? So I need to increase the profit by an additional 4, which is 8, before snow fence becomes part of the optimal solution. Right? Does this reduced cost column make sense? Yes, sir.
So is it saying if we increase production?
No, we increase the profit.
So the price. So
The price,
okay.
yes. Well, this is not the price. This is the actual profit that you're making.
So if you decrease costs or increase the...
Yeah, so either way. So whether you decrease cost or you increase the price, if your profits go up by 5.7 units or $570, then you will start making some roofing mesh. Yeah? So here we have two columns, the allowable increase and decrease, which is telling you how much you can increase the profits by or decrease the profits by before changing the solution. So what is the current solution? We are maximizing a profit at 34 units or $3,400, right? So if we increase the objective coefficient by say 4.1 units, so it becomes 10.1. Now the optimal profit is going to be different, and we have to resolve the entire problem to see what that is. Okay, so that's what this allowable increase is. If we increase our roofing mesh profit by more than 5.7, say 5.8, then the objective, the maximum is going to change. And so our new optimal solution can only be got by re-optimizing the whole thing. Now for a small problem like this, it doesn't really matter. But if we have a large problem that takes hours to solve, this information is really useful because now we can change these values within the ranges given to us, within the maximum increase and decrease, and see what outcomes are available. That gives us some sensitivity analysis room to wiggle, right? That's why this is so useful. So here clearly we can increase it by the allowable increase. So we can actually add these two to the solution, right? Now, one important thing to remember is we are in this class not going to do any sensitivity analysis because there are many rules that are involved in making simultaneous multiple changes at one time. Okay? Because if we add this, then something else has to be taken away. Because that's going to change the... So we are not going to study those rules. It takes an entire class to learn those rules. Okay? So we're not going to go there. Just know what these components of these different reports are. Okay? And what they do. Now, a really important one is constraints. Like I said, we had one non-binding constraint, right? The aluminium available. So you'll see over here, sorry, we had two binding constraints. We had the Y machine and the loom, and those are the important ones. And you'll see that for those binding constraints, we have something called shadow prices. Okay? And we have the right-hand side constraint that is going to be affected by the shadow price and the allowable increase and decrease, which allows these right-hand side values to either increase or decrease. Okay? Now here for the aluminium, you'll see that you can allow the right-hand side to increase to infinity because we have slack. Okay? And we can decrease it to 5 because once we decrease it below 5, then we have to re-optimize. The solution is no longer going to be valid because we use 10 units or 10 hundredweight of aluminium to solve the problem. Okay? So now, what is the shadow price? This shadow price, the way we interpret it is, for the Y machine, if we add 1 unit of Y machine capacity, so what is our 1 unit of Y machine capacity? 100 hours, right? So we add 100 hours of Y machine capacity, we increase our profit by 4 units, or $400, which is the unit of our profit. So, saying it in layman's terms, if we increase our Y machine capacity by 400 hours, if we increase our Y machine capacity by 100 hours, we're increasing our profits by $400. Okay? Similarly for here, if we increase our loom capacity by 100 hours, we're increasing our profits by $100. That's the meaning of shadow price. So this is an extremely valuable report to have when you have binding constraints, to be able to see where do you have the maximum bang for your buck, where can you invest in to increase the value of your system, right? And it tells you, for example, I can increase it by 1 hour. So it's telling me that I can actually increase my profits overall by $400, right? So if it costs me less than $400 to increase my my Y loom capacity by 100 hours, then it's clearly something that I need to, I can clearly invest in, right? Now, if I need to pay overtime and it changes the labor cost completely, then that's a different question, right? Okay. So, any questions about this sensitive report? Sam?
So what is the 1E plus 30 value?
So these 1E plus 30, that's just saying that it's a very, very large number. So it's going to infinity, basically. So you can decrease by an infinite amount. You can increase by an infinite amount. It's not going to have any impact on that. The reason for this being you're allowed to decrease this by any amount is because when you send this down to 0, it's not going to impact the problem anyways, because 0 profit means it's not going to be part of the solution anyways, right? And similarly here, because I'm not using all of my aluminium, I can increase the amount of aluminium available to infinity. It's not going to affect the solution.
So what kind of notation is that? It's not scientific notation.
That's just Excel scientific notation.
That is? Oh,
Yeah.
okay.
So what it is, it's 1 times 10 to the power of 30. That's what it is. That's the way you interpret that. Which is a very large number. Okay? Any questions about here? So here you can see that you have all of the different problems. You have the computer scheduling problem, then it's solved. You have the Lego simplex problem that I just showed you. You have the slick oil problem that we're going to learn next time. You have the transportation problem, and the transportation problem solved. This is pertinent to your homework. So, question?
Yeah, we were running through this before. How did you come up with the values in the red box?
Yeah, because it was the optimized solution from the.
This is the optimized solution.
But how did you
calculate?
So do you have to
values?
calculate it by hand and then input it, or?
These values?
Yes.
This is what Excel does for you. So, for example, I do solver here. Oh, let me go here. It'll be quicker if I can just delete these. Okay, I have solver set up over here already. So I delete those and I hit solve. And I say okay, and those the values are there.
Okay. And it's more some solvers that gives you those.
So Excel solver is what gives you those values.
Okay.
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 Easy peasy.
Yeah, that was a lot easier than what we're trying to do. Is the video going to be out before the homework is due?
It should be. So maybe I can give you all a Valentine's Day gift and say maybe the homework is due next Tuesday. Give you all some breathing room.
Yeah. Yeah.
All right? Next Tuesday?
Is that what you just said, or did I hear you wrong?
No, you heard me right. So I said I can give you a Valentine's Day gift and say, homework is due next Tuesday. How's that sound?
Sounds good.
All right, very good.
Are you going to everyone is office?
Okay, so couple of things to wrap up. So go through your notes. All of these things are there in your notes. I've given you some. We've looked at all of these. Now, sensitivity analysis, there's definitions for this, but before we take that down, make sure you do some basic sensitivity analysis over here with the Lego example. Okay? Just as practice, and we'll do it next time. Okay? Does sound good? All right, and there's definition for you all to take down. I promised you that we'd finish 5 minutes later, not 5 minutes earlier. Right?